A ball is attached to a string and swung in a horizontal circular path with a constant speed, and the force in the string is Ft, being the tension force. What is the magnitude of force in the tangential, radial, and vertical directions? Well, in the tangential direction, given that the speed is constant, the force has a magnitude of 0, and because this is a horizontal circular path, then this force has a component pointing to the center of the circle. So in the radial direction, the magnitude of the force is the mass of the ball by the square of the speed on the radius of the circle. And in the vertical direction, we have the vertical component being equal to the weight of the ball, which is the mass of the ball by the gravitational acceleration. And therefore the correct answer is D. A block with a mass m is accelerating up an inclined plane due to an applied force F. And what is the acceleration of the block? Now if we take the directions parallel to the plane and perpendicular to the plane and identify the forces acting on this block, we have the force of weight, the kinetic friction force opposing the motion, and the normal force preventing the block from sinking into the plane. So applying Newton's second law in the x dash direction, and recognizing that this angle and this angle is equal to the angle of the plane, we have F cosine theta minus the kinetic friction force minus the force of weight by sine theta to give the component in the x dash direction is equal to the mass by the acceleration. And applying Newton's first law in the y dash direction, we have the normal force minus mg cosine theta, so that will be equal to mg cosine theta, and minus f sine theta gives the vertical component acting downwards, so that will be plus f sine theta on the other side of the equation. So the kinetic friction force is the coefficient of kinetic friction by the normal force. So we end up with F cosine theta minus the coefficient of kinetic friction multiplied by the normal force, which is mg cosine theta plus F sine theta. And then we have minus mg sine theta is equal to the mass of the block by the acceleration. And now if we do a bit of algebra, we can divide through by m. So we have F on m, and that's multiplied by cosine theta minus mu k sine theta. And then we can factor out g. So we have mu k cosine theta plus sine theta. And that's thereby equal to the acceleration of the block. So the correct answer is B. A person with a mass m steps on a scale that's placed on the floor of an elevator, and we're asked to find the reading on the scale if the elevator is accelerating upwards at g on 2. So if we take a free body of the person, we have the normal force of the scale acting upwards, and we have the force of weight acting downwards, and the person's accelerating upwards with the elevator. So applying Newton's second law, we have the normal force minus the force of weight is equal to the mass of the person by the acceleration, which is g on 2. So therefore the normal force is equal to mg on 2 plus mg, which is 3mg on 2, which will be the reading on a scale. So the correct answer is B. A small block with mass m is sitting on a larger block with mass capital M and subjected to a force. What is the maximum acceleration such that there's no slip between the blocks? So no slip means we're looking at static friction, such that there's no relative motion between the blocks. And we can assume frictionless contact between the ground and a large block, and the friction coefficients for contact between the blocks are μs and μk for static and kinetic friction. So the static friction coefficient is going to be the constraint that prevents slip and results in a maximum acceleration. So therefore A and C are the potential correct answers. So if we take a free body of the smaller block, we have the force of weight, and we have a friction force acting in this direction, which is in the direction of the acceleration. So this is the static friction force. And we have the normal force acting upwards to prevent this block from sinking into the lower block. And if we take a free body off the larger block, by Newton's third law, we have an equal and opposite static friction force and an equal and opposite normal force. So these are the contact forces. And we have the force of weight acting at the center of mass and a normal force preventing this block from sinking into the ground. And we have the force F acting to the right. So if we apply Newton's first law in the vertical direction, we have this normal force is mg, and applying Newton's second law in the horizontal direction, we have the static friction force, which is μs mg, is equal to the mass by the acceleration. So therefore A is equal to μs times g. So this is the maximum acceleration that can be achieved, which is constrained by the static friction coefficient. And by Newton's third law, this static friction force is equal in magnitude to this static friction force, but acts in the opposite direction. So applying Newton's second law in the horizontal direction, we have minus μs by mg plus F is equal to the mass by the acceleration. So therefore the acceleration is 1 on m by F minus μs by mg. So therefore the correct answer is D. A box with a mass of 3 kilos is attached to a roof by 2 cables. Calculate the magnitude of the forces in both cables. So if we isolate the block and take a free body, we have the force of weight and a tension force in the left cable and a tension force in the right cable. And applying Newton's first law in the horizontal direction, we have Fr cosine 45 degrees minus Fl by cosine 60 degrees is equal to 0. And applying Newton's first law in the vertical direction, we have Fr sine 45 degrees plus FL by sine 60 degrees minus mg is equal to 0. And therefore from this equation we have FR is equal to cosine 60 degrees on cosine 45 degrees by FL, which is 0.707 FL. And substituting this into this expression, we can solve for FL. And we were given a mass of 3 kilos in the problem, and the gravitational acceleration is 10 meters per second squared. So therefore we get FL is 21.96 newtons, which when substituted into here gives FR is equal to 15.53 newtons. So the correct answer is A. What is the tension in the cable attached to the two masses on the right, being these two masses? And we're told that all blocks have the same mass and coefficient of kinetic friction. So if we treat these 3 blocks as a system, so we treat them as a particle, so therefore the external force acting on this particle is F. The kinetic friction force between the ground and each of these blocks, so this is the total kinetic friction force. And we have the normal force being the total normal force acting on these blocks, and the total force of weight. So applying Newton's first law in the vertical direction, we have the normal force minus the force of weight. So if we take the mass of each block as m, we have 3 blocks by m, where the gravitational acceleration is equal to 0. And applying Newton's second law in the horizontal direction, we have the kinetic friction force acting to the left, which is a kinetic friction coefficient, by the normal force, which is 3 mg. And plus F is equal to the mass of the system by the acceleration. And because we want the tension in this cable, so our free body diagram in this case would be used to isolate the left 2 blocks. So we'd have a kinetic friction force of minus mu k by the normal force due to the contact between the 2 blocks and the ground, which is 2 mg, plus the exposed tension force in the cable is equal to the mass of the 2 blocks by the acceleration. So if we divide the first equation by 3 and the second equation by 2, and then equate the 2 equations, we have minus mu k by mg plus F on 3 is equal to minus mu k mg plus a tension force on 2. So therefore the friction forces cancel, and we end up with the tension force is 2/3 of the applied force on the right block. So the correct answer is B. A 3 kilo ball is rolled up a frictionless plane with an incline of 40 degrees, and the initial velocity is 10 meters per second, which is directed along the incline. Find the distance that the ball travels. We'll recall the kinematic equation, which involves the velocity. So we have v squared is v naught squared plus 2 by the acceleration by the displacement. So that will be the distance travelled by the ball. And now we want to find the unknown acceleration of the ball. So we'll choose our coordinate system using the axis parallel and perpendicular to the plane. So there's a force of weight acting on the ball, which is the mass by the gravitational acceleration, and we have a normal force preventing the ball from sinking into the plane. And applying Newton's second law, we have the acceleration that's parallel to the plane, acting in a direction of the net force, which is mg sine theta. Noting this angle is equal to the angle of the plane, and that's equal to the mass of the ball by the acceleration. So therefore the acceleration here is g by sine theta, which is 6.248 meters per second squared. And noting this acceleration points to the left, we have the final velocity squared is equal to the initial velocity squared plus 2 by negative a, which is minus 2 by 6.248 by d. And then solving for d, we get 7.8 meters. So the correct answer is D. Two blocks are attached by a cable and pulley system, as shown, and a small and large block has a mass of 2 and 5 kilos. Calculate the magnitudes of the force in the cable and acceleration of the blocks, and assume a frictionless surface and a massless cable and pulley. So if we take a free body of the left block, we have the force of weight being 2 kilos by 10 meters per second squared, and the normal force and the tension force in the cable. And for the larger block, we have the force of weight being 5 kilos by 10 meters per second squared, and the tension force in the cable has a smaller magnitude. So this larger block will accelerate downwards, while this smaller block accelerates up the plane. And we'll note the angle of the plane over here as 35 degrees. So recognizing the angle of the plane is equal to this angle, and applying Newton's second law in a direction parallel to the plane, we have the tension force minus the force of weight sine 35 degrees is equal to the mass of the smaller block by the acceleration. And applying Newton's second law to the larger block, we have minus the tension force plus 50 newtons is equal to the mass of the larger block by the acceleration. So if we add these two expressions together, the tension force cancels, and we have minus 20 sine 35 plus 50 is 7 by the acceleration. So if we solve for the acceleration, we get 5.504 meters per second squared. And if we substitute this into this equation, we get the magnitude of the tension force, which is 22.5 newtons. So the correct answer is C. A skydiver opens his parachute, and from this instant, he has an initial velocity v0. Now the system, being the parachute and skydiver, has a mass m, and which is the correct ordinary differential equation that models the system for the case of linear drag, where the acceleration is proportional to the velocity, with the drag constant being the constant of proportionality. So initially, the acceleration will be downwards. So we have the force of weight minus a drag force is equal to the mass of the system by the acceleration, being the derivative of the velocity with respect to time. So the correct answer is either C or E. Now the terminal velocity is obtained when the acceleration goes to 0. So therefore, we end up with mg minus k by the terminal velocity is 0. So therefore the terminal velocity is mg on k. So the correct answer is E. A car is travelling around a bend with a radius of 20 meters at a constant speed. Calculate the maximum speed to complete the turn without skidding, and the friction coefficients are given below. So taking a free body of the car, we have the force of weight being the mass by the gravitational acceleration, and the normal force and the static friction force provides the centripetal acceleration. So applying Newton's first law in the vertical direction, we have the normal force is equal to the force of weight. And Newton's second law in the radial direction gives the static friction force being equal to the static friction coefficient by the normal force is equal to the mass of the car by the centripetal acceleration. So therefore the maximum speed to make the turn without skidding is equal to the square root of the static friction coefficient by g by r. So if we take the gravitational acceleration as 10 meters per second squared and substitute the values given in the problem, we get a maximum speed of 13.4 meters per second. We'll go through some of the main topics that you should be familiar with in Unit 2, being Newton's laws of motion. So be comfortable with adding vectors and resolving the vector components in different coordinate systems, which is useful for inclined planes. And be familiar with adding and subtracting vectors, and also scaling vectors, as well as taking the magnitude. And know how to isolate objects and draw free body diagrams with the main forces acting on the object. And these main forces are the tension force, friction force, normal force, and the force of weight due to gravitational acceleration near the surface of the Earth. And note that the friction force can be static friction or kinetic friction, depending on whether the object is moving or static. And the friction force is a fraction of the normal force, which is obtained using the friction coefficients. And be familiar with Newton's laws of motion, being the second law, where the net force acting on an object is equal to its mass by acceleration. And if the acceleration is 0, where the object's moving at a constant velocity, or the object is stationary, we obtain Newton's first law, which is the net force acting on the object is equal to 0. And know how to apply Newton's third law by identifying action and reaction pairs. So for example, the gravitational force exerted by the smaller object on a larger object is equal and opposite to the gravitational force exerted by the larger object on the smaller object. So the forces have the same magnitude, but the smaller object will have a higher acceleration. And be familiar with cables and pulleys, such as the outward machine, where you can draw free body diagrams that include the tension force in the cable acting on each object. And be familiar with inclined plane problems and know how to resolve the forces in different coordinate systems to simplify applying Newton's laws of motion. And know the drag forces, which are the resistive forces other than friction. So if you have linear drag, you use the first expression, and in the second expression, you have parabolic drag, where the magnitude of the drag force is proportional to the square of the speed of the object. And know how to construct a differential equation. So for example, if you have a skydiver opening his parachute, and using the gravitational force and the drag force, and the acceleration being the derivative of the velocity with respect to time, you'll be able to construct the ODE and obtain a terminal velocity, where the terminal velocity is where these two forces balance and the acceleration is 0. And be familiar with horizontal circular motion versus vertical circular motion. And in particular, when we look at horizontal circular motion, the speed of the object is typically constant, so the tension force in a string will only have a normal component pointing towards the center of the circle, and a vertical component to resist the gravitational force, and these two components keep the object traveling along the horizontal circular path. And know the relationship between a centripetal acceleration and the speed of the object. And in the case of vertical circular motion, you have a gravitational force acting on the object, so therefore the motion will be non-uniform, and you'll have a tangential acceleration being the rate of change of velocity of the object, as well as a centripetal acceleration, which is also v squared on r. So if you have any problems with these topics, see the linked playlist below, where we cover them in more detail. A block with a mass m is subjected to a force and slides horizontally. And what is the acceleration of the block, given the kinetic friction coefficient? Well, first we isolate the block, taking a free body. So we have the force of weight, the normal force, the kinetic friction force, and the applied force F, which is applied at an angle of theta. So applying Newton's first law in a vertical direction, we have the normal force minus the force of weight plus the vertical component of the force F. So that will be F sine theta. And that's equal to 0 because the block's sliding horizontally. And applying Newton's second law in the horizontal direction, we have the force F cosine theta minus the kinetic friction force. So that would be the kinetic friction coefficient multiplied by the normal force, which is mg minus F sine theta. And that's equal to the mass by the acceleration. And now if we divide through by m and factor out the force, we have cosine theta plus mu k sine theta and minus mu k mg on m, so that would be minus mu k by g. And that's equal to the acceleration of the block. So the correct answer is A. A ball with a mass of 3 kilos is rolled up a plane with an incline of 40 degrees. Find the magnitude of the acceleration at the time instant shown, and assume the following values for the static and kinetic friction coefficients. So taking a free body of this ball, we have the gravitational force acting downwards, which is 3 kilos by 10 meters per second squared, and the normal force, and the kinetic friction force acts to the left, parallel to the plane. So we can choose our coordinate system to be parallel and perpendicular to the plane. And the acceleration is going to be acting to the left, in the direction of the net force. So recognizing that this angle theta is equal to the angle of the inclined plane, we can apply Newton's first law in the y dash direction. So we have Fn minus mg cosine 40 degrees is equal to 0. And applying Newton's second law in the x dash direction, we have the kinetic friction force, which is the kinetic friction coefficient, by the normal force, being 30 cosine 40 degrees, and plus the force of weight, sine 40 degrees, is equal to the mass by the acceleration. So if we solve this for the acceleration, we get 7.96 meters per second squared. So the correct answer is C. A ball is attached to a string with a length L and rotated anti-clockwise in a vertical circle. So that means the ground is somewhere here, given it's a vertical circle. And at the bottom of the circle, what is the rate of change of speed of the ball? Well, here we have the force of weight acting downwards and the tension force acting upwards. So because there's no net force in the tangent direction at this point, then the tangential acceleration is 0, which is the rate of change of speed of the ball. So the correct answer is D. A ball is tied to a string of length r and swung along a vertical circular path. Find the critical speed to prevent the ball from falling inside the circle. So at the top of the circle, with a radius of r, we have the tension force in the string acting in the same direction as the force of weight. So therefore the tension force plus the force of weight is equal to the mass by the centripetal acceleration. And the critical speed is when there's no tension in a string. So that's when Ft is 0. So solving this equation, when Ft is 0, we end up with the critical speed of root gr. So the correct answer is C. A car with a mass m is travelling at a constant speed around a bend with a radius r. And the road is banked at an angle theta. And we're asked to write the normal force in terms of the mass and speed of the car, the radius of the track, and the banking angle. So taking a free body of the car, we have the force of weight, the normal force, being perpendicular to the road, and the friction force being the static friction force that's parallel to the road. And this angle here is equal to this angle, which is equal to the banking angle. So if we apply Newton's second law in the radial direction, we have the static friction force by cosine theta plus the normal force by sine theta is equal to the centripetal force. And in the vertical direction, we have the static friction force sine theta. So this has a vertical component pointing downwards, plus the normal force cosine theta, and minus the force of weight is equal to 0. So we can put the force of weight on the other side of the equation. And because we want to eliminate the friction force, given that we want to determine the normal force, we multiply the first equation by sine theta, and the second equation by cosine theta. So we have sine theta and sine squared theta and mv squared by sine theta. And in the second equation, which we'll multiply by cosine theta, we end up with cosine squared theta and mg by cosine theta. So if we add these two equations and use the trig identity, we end up with the normal force on the left hand side, and factoring out m, we have v squared on r sine theta plus g cosine theta. So the correct answer is A. What is the advantage of banking the road surface of a racetrack? And in part A, both the normal force and static friction force contributes to the centripetal acceleration. So this is true if we take a free body of the car. We see the normal force and the static friction force being oblique to the radial direction, and the force of weight points downwards. So part A is true. And part B refers to the kinetic friction force, which is not true, as the static friction force is the one that prevents slip in a radial direction. And in part C, the car can travel faster around the bend, which is true, because both the normal force and static friction force provide the centripetal acceleration. So we have the static friction force cosine theta plus the normal force by sine theta is equal to mv squared on r. So therefore, if there's no banking angle, then this second term would be 0, and only the static friction force would contribute to the centripetal acceleration, and the maximum speed that the car can travel around the bend would be smaller. And part D is incorrect, because we've identified part A and part C as the advantages. So the correct answer is E. Which of the following are action-reaction pairs? So remember, by Newton's third law, an action-reaction pair is the same type of force with an equal magnitude but an opposite direction. So in part A, the normal force and the force of weight is not an action-reaction pair, but rather the normal force exerted by the ground on the ball forms an action-reaction pair with the normal force exerted by the ball on the ground. So we can ignore A. And in part B, we have a gravitational force between two objects, which is equal in magnitude and opposite in direction. So B is correct. And in part C, the friction force exerted by the ground on the ball is equal and opposite to the friction force exerted by the ball on the ground. So C is also correct. And D is also correct because we have the same electrostatic force that's equal and opposite between the two charges. So E is the correct answer. If n blocks, each having a mass m, are connected in series and subjected to a force F, what is the tension force in the cable on the right of block K? So here we have block K equals 1, K equals 2, up to K equals n. And the coefficient of kinetic friction between the block and the surface is the same for all blocks, and all the blocks have the same acceleration. So if we treat all these blocks as a system, with the forces acting at the center of mass, we have the force F, the total normal force, the force of weight, and the kinetic friction force. So applying Newton's first law in the vertical direction, we have the normal force minus the force of weight, which is n blocks, multiplied by the mass of one block by the gravitational acceleration, is equal to 0. And applying Newton's second law in the horizontal direction, we have the kinetic friction force is minus mu k by the normal force, which is nmg, plus the force F is equal to the total mass of the system by the acceleration. And now if we cut a cable after block K, we'd expose an internal tension force, so the free body diagram would have Ft instead of F. And the kinetic friction force would be mu k multiplied by k blocks by mg plus Ft is equal to k blocks by the mass of one block by the acceleration. And if we divide equation 1 by n and equation 2 by k and subtract the two equations, the friction terms cancel and we'd have F on n minus Ft on k is equal to 0. So therefore, the tension force acting to the right of block K is K on n by the applied force F. So the correct answer is C. A cylinder with a radius r is rotating anti-clockwise about its axis at a constant angular velocity. And a particle is pinned against the wall due to the centrifugal force. And what condition must hold to stop the particle from sliding down the wall? And we're given the static and kinetic friction coefficients. So if we take a free body of the particle, we'd have the normal force, the force of weight, and the static friction force. So for the ball not to slide down the wall, the static friction force must be greater than or equal to the force of weight. So in this case, the normal force provides a centripetal acceleration by Newton's second law, and the static friction force is the static friction coefficient by the normal force, being mv squared on r, and that must be larger than or equal to the force of weight, which is mg. So if we solve this inequality for mu s, we get mu s is greater than or equal to gr on v squared. And given that the speed is equal to r by the angular velocity, we obtain gr on r squared omega squared, which implies mu s must be greater than or equal to G on R omega squared. So the correct answer is A. A car with a mass m is travelling at a constant speed v around a bend with a radius r, and the road's banked at an angle theta. What is the banking angle that ensures the car makes it safely around the bend, assuming a very slippery surface? So this condition means that the static friction force is close to zero, and the normal force is the one that provides the centripetal acceleration. So if we take a free body of this car, we have the normal force and the force of weight. And this angle here is equal to the banking angle. So applying Newton's second law, we have the normal force by sine theta is equal to the mass by the centripetal acceleration. And in the vertical direction, we have the normal force by cosine theta minus mg is equal to 0. So that's equal to mg. And if we divide the two equations, we get sine theta on cosine theta, which is tan theta, and that's equal to v squared on gr. And therefore, taking the arctan of both sides, the correct answer is C.